Thank you very much, Andre. First of all, I'd like to thank Andre and Yandex for inviting me to this workshop, which gives people a space to sit and think about problems in random graphs for a while, and to thank Alexandra and Julia for the organization, because I'm sure I caused them quite a lot of trouble. And it's actually my first time to come to Moscow, so I think that'll be very interesting as well, because I've already seen that there's a lot to see, so it's going to be, there's lots to do. Okay, so as Andre says, this is a more mathematical talk, and if you can't hear, let me know, because I'm not totally trusting this this mic that I've got here. So what is this talk about? Well, it's about you've got a random graph, and on this random graph is a random walk, and as the random walk proceeds, it visits vertices, so they're, in a sense, they're visited. And what does the part which is unvisited look like? So what is the structure of it, and how large is it? And so basically it's a sort of double randomness. Where's the... Okay, yeah. And okay, so what I'm going to do is I'm going to sort of define in more detail the sort of the idea of the vacant set, or the unvisited set. It's the set, I suppose this word must come from sort of percolation or something, but it's just a word which initially we weren't aware of this word, but it seems to be the kind of standard term for the part of the graph which the random walk hasn't visited. So it's the part which the graph hasn't visited, and sort of talk about the main results, and then I need to sort of talk a bit about random walks and the notion of cover time, because this was a kind of byproduct of a study of random walks, which in itself actually was just, we didn't set out to do it, but we kind of discovered it by mistake. So this is a sort of double chance, really, that we ever ended up here looking at this particular topic. And then I'm going to sort of talk a little bit more in detail about the structure of the vacant set for graphs GNP, and for used as a kind of model for a kind of a truncated version of the infinite R regular tree, and it's the kind of structure of the infinite R regular tree which makes it possible to analyze them, really. Okay, so this is a picture of a random walk on a toroidal grid, and each pixel in that picture has 4 neighbors: north, east, south, and west. And at the beginning, the walk started at the middle, and it made its way around the graph in some sort of way. And after a certain time, you can see that some vertices are visited, they're colored black, and some vertices are unvisited, they're colored white. And the principal question for random walks really is, how long does it take to visit all the vertices? And just in terms of that, at the moment there's a very large set of unvisited vertices, and so a primary question is, how does the size of that set change as the walk proceeds? And I must say that although I've drawn this in terms of the toroidal grid, the toroidal grid is actually very hard to analyze. We can only really make the kind of detailed analysis of this talk for random graphs. But the picture is nice. So as in the next figure, as the walk proceeds, you can see that it looks rather like sort of ice melting on a pond, that somehow there's a large series of components which are unvisited, separated by a kind of the visited walk. And this picture is completely untypical of what I will talk about here, because in the case that I discuss, there's only, I mean, you can see there's many large components in that, whereas in the case that I discussed, there's only one, with high probability, only one large component. So this is not, it's a nice picture, but it's atypical of the results for the talk. Okay, so the notation is that we have a finite graph with some vertices and edges, and we have a simple random walk on the graph starting at some vertex. So by a simple random walk, I mean that at the next step, a transition along each edge is equally possible. So it just chooses an edge uniformly at random and moves to a neighbor. The vacant set is the vertices not yet visited by the walk. And we can think of the vacant set as having one color, say red, and the visited vertices as having another color. So basically the graph is originally red, and as the walk proceeds, it colors the vertices blue. And so the primary question is how many vertices are unvisited at a given time? And the secondary question is, if I take the set of vertices which are unvisited and I look at the subgraph on the ground graph, on the fixed underlying graph induced by those, what is the structure of that graph? So I'm using RT as the vacant set at time t. So if I stop the walk at a particular time, how many vertices are unvisited, and what is the structure of the graph induced by the vertices which are unvisited? And so they're the two primary questions which we sort of got quite interested in addressing. So in a sense, it's like a random graph process in reverse, because originally there's the underlying graph, and none of the vertices have been visited by the walk. And when the walk starts, the initial vertex is visited, and as the walk proceeds, the number of visited vertices can only increase. It's certainly none decreasing, because as time goes on, you visit more and more vertices, and the number of vertices will decrease from all unvisited to no unvisited. So as the walk progresses, the vacant set is reduced from the whole graph to a graph with no vertices. And if you think about random graphs, well, in random graphs, small sets of vertices don't induce many edges. So as the number of vertices left unvisited becomes sparser and sparser, the number of edges induced by them must reduce, because that's just a property of random graphs, that the smaller the set, the sort of smaller the number of edges induced by the set. So it's going to get sparser and sparser as time goes on. And so you might think at some point, if it becomes very sparse, it will start to break up. You can imagine this as a sort of like a kind of an insect eating through a piece of wood or something. The more it eats, the more fragile the piece of wood becomes, the more it tends to sort of break. And at some point it will actually break, perhaps. But it'd be very unlikely that it would remain connected just until the last step, unless it was the complete graph. So as the walk proceeds, it's going to break up. And the question is, does it break up? Is there a kind of threshold time that it breaks up at? So it's like a random graph process, that there is a threshold. You know, before this time there was a giant component, and after this time there isn't a giant component. Or is it just that, you know, there's the distribution of times where it breaks up is not very concentrated, so it can happen over a wide range of times. So basically we're asking, does it exhibit threshold behavior? And we need a bit of notation. So I'm going to say that the graph induced by the vacant set, or the unvisited vertices, is subcritical if all its components are of size at most a logarithm. And I'm going to say it's supercritical if it has a unique giant component. In other words, when I say a giant component, it may not be the size of the graph, but it will be of the order of the unvisited set, so RT, it will be the same order as the unvisited set. and all the other components are of logarithmic size. Oh, you've got a question.
So, so I gather then you're not going in the window because inside the window, I mean, if I took my time to be a function of n, then I could have components which are larger than log n and yet not have a single giant component, right? So your t is
it's a coarse
uniform in n.
It's well, it's a coarse threshold.
It's a coarse threshold.
Yeah, I mean. Okay, so we just proved a coarse threshold. I will mention some other people sort of improved that to show, because I think, I remember Christian asking me this question before when I was thinking about something else, which was a bad moment for me, but and no, I'm going to give a very coarse threshold, so it's like almost a constant or something tending slowly to zero. I'm not going to do the precise thing. It was more we were sort of, but when we first thought about doing this, we didn't realize it had been studied by other people. So it was more a sort of curiosity to see what happened. You know, was there a sort of value around which it drops to bits? But it's very much in the sort of the early days of Erdos-Renyi where, you know, there's a threshold around p equals 1 over n. And if it's a little bit less, then everything is logarithmic. So in this case, if it's a little bit more, everything is logarithmic. And if it's a little bit more, then there's a giant component in our case if everything's less. But we're not looking very carefully in the scaling window. This is very much a sort of, early days talk. So, okay, so when we say this T star, what I mean is, it's around that value. It's not precisely explained there. We're not saying there's a precise T, but we're saying there's a value around which it drops from supercritical to subcritical. How do you do the page up on this thing? If you want to move a page up as opposed to down, how do I move the slide back up?
He wants to know how to go backwards.
How do I go backward on this thing? Oh, use that, yeah? Okay, so on here we, right, so here we have, basically there's some sort of T around which something happens, and we're not going to say it very precisely, but we will say something. So basically, the way it's just phrased here is a small constant or tending slowly to zero, that if it's slightly below this kind of some magic value, then it's got a giant component. And if it's slightly above this magic value, then everything is logarithmic. That's all that we proved. And basically for Erdos-Renyi type graphs, and we're thinking now of above the connectivity threshold, and we're thinking a little bit above it really, so that this number is greater than 1. In fact, c minus 1 times log tends to infinity. So it's not on the connectivity threshold, but it's a bit above it. And we're saying that c is not too big because we didn't really analyze it for c big. We just sort of did it up to that value. So it's quite a partial analysis that we did. Then you can find a value t, which is a function of it, and you can parameterize it by epsilon. And so this value t is like n times log n, so it's a little bit larger than n, and it's also got a log c there, and this can be, so that can be quite a large thing, that log c.
So can you do c equals 5?
Yeah, do c equals 5, yeah, but not c equals n, basically.
Okay, so you can do just the simplest imagining thing would be c equals 5. Then I know I have sort of a random graph with one component, everybody is connected. And now you do your random walk, and then you actually then know this threshold quite precisely, because you have the log n.
Yeah.
But you say as soon as c grows faster than log n.
No, we didn't say that. We said c, n to the o of 1. So I'm not offering to do n to the half for c, for example.
No, but if c log n would be little o of 1, right?
Yeah.
So if c would be equal to log n,
Yeah.
then actually your first term is dominated by the second. So in one case you have a shift in one, in the other you don't. That's
Well, it's probably sloppy notation. What I mean is that I mean n to the whatever, not to n to the constant, right? I don't want to do n to the constant. Okay. It's crummy notation, but
so you want log n to some power essentially.
yeah, I'm not too fussed about this. It's just we didn't push it through. We didn't do it for the complete, you know, as it tends to.
But if I would just think that C is between, so C should be at least 1, okay, otherwise your first thing is violated. And otherwise it should not grow faster, let's say, than log n to the 500.
Well,
yeah,
okay.
good.
Okay, look, I'll tell you in a minute, right? But the fact is that if you ramp C up too much, then you'll get to a point where the number of vertices left when you're looking at the threshold is less than log n, so you won't have any sense. They're talking about supercritical and subcritical. So it's just designed to kind of sweep that under the carpet. I mean, the precise value of C we didn't look at in the upper bound. We didn't really care. But okay, so basically there's definitely a giant component up to at least n log n. And for the values of C that we choose, C greater than 1 constant, random graphs GNP have a cover time which is basically n log n. So it gives you a clear idea where things are. It doesn't drop to bits until superlinear in n, and by the time you get to n log n, everything is gone, because for those values of C, the cover time is n log n. And I'll explain the cover time. I'll define it properly in a minute. Okay, and just to contrast this, for random graphs, our regular random graphs, for r greater than or equal to 3 constant, the critical value, which here was basically n log n plus something, where the something is open to argument. The critical value here for our constant is basically some constant times n, so it behaves rather differently, or so it might look. Although actually, if you take the r is expected degree, so you might sort of think that if you put r in there, you'd get log n, log of log n, which would be log n times n if you took p equals log n. So it's very similar actually. And once again, below that value there's a giant component, and above that value it's subcritical, so everything is just logarithmic at most, little bits. And as an example, if you take 3 regular random graphs, then that critical value is at 6 log 2n, and so there's a giant component up to about 6 log 2n steps, and then it drops to bits, and everything is logarithmic. And to contrast that, the cover time of a 3 regular random graph is about 2n log n. So that's quite early compared to that, whereas the other one was quite late. So it's basically, because this is sparser, it looks different, okay? So if you push the value of r up to, say, a log n, then it would probably look pretty similar to GNP.
So that's interesting, because you couldn't...
Well, but we didn't go there. We didn't go there, Christian, so it's like...
I see. So did you prove this theorem or not?
Yeah, we proved this.
What
do you think I've talked about?
So given that you proved that theorem, you actually prove more for the 3 regular ones, because now you have actually constant degree, whereas in the other case you actually needed degree log n, right?
Yeah, we just want connectivity. Otherwise, the random walk's not going to do anything. I mean, you could walk on the...
But in the 3 regular case, you don't have connectivity necessarily, do you?
Yeah, with high probability it's connected, yeah.
I see.
Yeah. You can sort of make analyses on the giant component, but I'm just going to stick with this for this talk. So 2 classes of graphs. We worked out what the vacant set was and what it looked like, and that entertained us for about 20 minutes. Okay, so this very different results. Previous work, right, well, when we started we didn't know any of this, but there's been quite a lot of previous work actually, and concurrent work. So Benjamini and Schnitzman and Windisch considered the d-dimensional torus for large D, and they showed that it has, similarly, has a threshold value, which is it's difficult to obtain for the torus. And it's certainly for the two-dimensional torus it doesn't, because the pictures I showed you at the beginning showed many large components. It didn't have a threshold. So it only worked for d greater than or equal to 3. And they used a concept of random interlacements, which so they use continuous, negative exponential waiting time random walks, and a concept of random interlacements. It's completely different the way it's proved. And Czerny, TXR, and Windisch did actually consider R regular random graphs, and they had the same value of T star, and they showed subcriticality above the threshold and the existence of a unique giant below the threshold, but they didn't prove that everything else was logarithmic. And these proofs use the concept of random interlacements of continuous time random walks. So if you like, some of this work was done by other people in parallel using different techniques. But this is the talk here is a very sort of in the spirit of random graphs, discrete, simple type process. Our proof is based on steps in discrete time. It's simple. It's based on established random graph results. So basically, we analyze something and then use a theorem of Malloy and Reed, which is an existing theorem, or just simple theorems about the structure of GMP. It gives results for GMP, which was previously unanalyzed, completely characterizes the component structure, well, the tree component structure anyway, proves that in the supercritical phase, the second largest component is order log, and gives the structure of the small trees, so we know what all the little bits look like. And subsequent to this, answering Christian's question to a certain extent, Czerny, TXR, and Windisch considered the R regular graphs GNR, and they investigated the scaling window T star using, I've called this the annealed model, but it's not the annealed model we were talking about earlier on. It's another annealed model. This is our annealed model, which I'll explain. But that's the same model, yeah?
So using the annealed model, that's a proof technique, not a result.
Yeah, it's a proof technique. I mean, the annealed model to us is we use the random walk to reveal the graph. So the graph is basically, it's generated in the configuration model, and the random walk reveals the graph. So annealed means we don't, when Czerny, TXR, and Windisch first did this, they fixed the underlying graph, and it makes it harder to analyze than if you use the walk to reveal the graph. So yeah, basically this is what I mean by that. It doesn't mean anything. It's use the walk to reveal the graph. Sorry, I'm not addressing the whole audience here, but what they proved, as far as I can remember, was that in a scaling window of around n to the 2/3 of that value T star, the component size, the maximum component size is n to the 2/3 in that window. So as the walk is actually dropping down, the number of unvisited vertices is decreasing every now and then, and when you get in the scaling window, it's n to the 2/3. So they kind of came up with the details of that using sort of more sophisticated versions of the Malloy-Reed theorem. Okay, so the proof technique is as follows. Basically, we use the walk to reveal the graph, and that's what we call the annealed model. Or that's what we were told it was called, okay? We don't actually, that's our name for it. What we have, the technique is we estimate the probability that a vertex hasn't been visited by the walk, and hence the size and degree sequence of the vacant set. So we estimate for the unvisited vertices how many of their neighbors are visited and how many of their neighbors are unvisited. And then basically, once we know the degree sequence of the vacant set, the graph induced by the vacant set is random because we haven't revealed it, and given the degree sequence, we can use the Malloy-Reed condition for the existence and size of the giant component in a fixed degree sequence graph. So if we can get the degree sequence of the vacant set, we can use this off the shelf to find the size of the giant, and when it disappears, And in getting the degree sequence, the technique we use also works for counting small unvisited trees, all of whose neighbours are visited. So basically, this is a kind of... So the basic problem is how to estimate the probability that a vertex hasn't been visited by a random walk. That's the basic problem here. Okay, so just sort of diverging a little bit from the central talk, to talk about the cover time of a graph by a random walk. So the cover time of a graph, I have to draw a picture here, is I've got a graph and I've got a random walk starting at some vertex u, and the cover time t cover starting from u is the expected time for the walk to visit all the vertices, and the cover time is the maximum of that expectation over all vertices. So for some sorts of graphs, like a path, the cover time depends on where you start. If you start here, it will cover it much faster than if you start there, because you have to go there and then come back. So where you start matters for some graphs, but for the graphs that we look at, it doesn't actually matter. So it's the answer is going to be this. The cover time is essentially the expected time to visit all the vertices starting from any vertex for the graphs that we look at. It's not sensitive to structure. So this can be done for any connected graph. So the cover time of a random walk is the maximum expected time over all start vertices for the random walk to visit all the vertices of the graph. And ever since kind of people thought of random walks as good ways of searching large networks or crawling them, then there was quite a lot of interest in cover time, because it's a technique you can use on kind of third-party networks as long as you don't overexpose, the sort of, don't make too many sort of demands on the network to sort of crawl around inside it. So it's a technique of interest. It has practical value, and it also is of considerable theoretical interest, because it's a natural question. The random walk sets off, how long does it take to go everywhere? And you might think actually that it's not a very good way to do things, but for many graphs, a random walk is quite a good way to search it, because for expanders on n vertices, typically you can search the graph in n log n time, which isn't much more than the size of the graph. It's just a log factor times the graph. So it's a nice technique for searching graphs which are well connected. Purely by coincidence initially, we studied the cover time of random walks on various types of random graphs. Our original interest was in is sort of how, crawling these things. The graph is growing, the walk is walking. How much can we crawl? This is where it all started, but we ended up here instead. There's a sort of series of results which you can prove, and you can prove very precise results for the expected time to cover all the vertices. So, for example, in Erdos-Renyi graphs above the connectivity threshold, the cover time is basically some function of the average degree times n log n. So if this function if c is quite close to 1, then this function actually adds a bit to it. Whereas if c is a constant above 1, this function more or less disappears, or c tends slowly to infinity, and you get n log n as the cover time of the graph. And you can also analyze random regular graphs for R at least 3, where it's connected with high probability. These are with high probability results. And with high probabilities on the graph, because for most graphs this is true, that the cover time is some function of the degree times n log n. So when R is 3, that function comes out to 2, and as R tends to infinity, that function just tends to 1. So you can kind of write down quite accurately what the cover time of these graphs is. And maybe of interest to this workshop, you can also do this for web graphs, in other words, preferential attachment graphs, where you add at least 2 edges at each step. So if you do that with a preferential attachment graph, you get a cover time of, the graph is growing, but if you stop it at some time t, then it's some constant times t log t. And this proof actually comes from the regular case by finding a kind of blocking structure to the walk, which are basically R regular trees or R+1 regular trees. And you can also do the cover time of directed graphs. So this was, but this was a bit more of a challenge. So for directed graphs NP, the problem actually for directed graphs is unless the in degree is equal to the out degree for every vertex, it's very hard to put a hand on the stationary distribution of the graph, of the random walk. It has a stationary distribution, but it's difficult to work out what it is. But as long as the kind of the average degree is at least, the average directed degree is at least some constant times log n, where the constant's greater than 1, or then basically the stationary distribution of a simple random walk on a strongly connected DNP is just the in degree divided by the number of edges. So if you let NP tend to log n, then you need to consider not just the in degree, but the in degree of the second neighborhood and so on. It becomes more and more complicated to compute. But this is the stationary distribution of a random walk on a strongly connected DNP. So that's just the directed version of the Erdos-Renyi graph. Yes, go ahead.
I have another question here. When I looked last at the random directed graph, but it's a long time ago, there was some proof at some point about the threshold, I think by Karp and other peoples, and when I tried to analyze that, it turned out that there were some little mistakes in it. So did you have to deal with that, or does that not come up when you are above this normal threshold?
Well, basically it will come out of the proof technique here, because we constructed paths between every pair of vertices, so it's strongly connected by the construction we use. Because I mean, the problem is not this. I mean, the technique which we sort of came across by mistake does all sorts of graphs, because it's just about recurrent processes. So you can throw, as long as you know the parameters of the graph, you can kind of throw it into the technique. But the problem's here. The problem's deriving the stationary distribution. And to derive the stationary distribution, we constructed a sort of a branching out, an out branching and an in branching, and stuck them together between every pair of vertices. And you had to kind of measure the flow through this branching. There was a real lot of fiddling about it. It was absolutely awful. It took about 6 years to get it right.
That's where the Karp mistake was.
Yeah.
Exactly that.
Yeah. Okay.
So
well.
you probably fixed that.
Yeah, but we didn't.
That was a real mess.
Yeah, well, we didn't.
You assume more independence than you had between the in and out trees, because after a while they don't become quite independent. You have to control them.
Yeah, because I mean, well, the problem is when you're fanning out, some of your fan in is also turning up inside the fan out. I mean, it's starting to, yes, I mean, actually the interesting result is this one. Yeah, that the stationary distribution is that. Okay, so you can get the cover time of things, and the method to get the cover time basically evaluates the probability that a vertex is not visited. So this is the basic idea, and vacant set is a kind of byproduct of this idea. So we only consider rapidly mixing graphs because we want to know that after a logarithmic number of steps, for example, the walk is just anywhere, or it's got an almost stationary distribution. It may not be quite stationary, but it's almost stationary. So to estimate the unvisited, and this, I mean, it's a bit of this is oversimplified the way it's explained here, but to estimate the unvisited probability, that's the probability that the state hasn't been visited after t steps of the process. Well, actually, that's a bit of a problem, because when the walk starts off, it certainly visits the start vertex, and the stuff around it's got a good chance of being visited. So after a while, it's easier actually just to kind of sweep that under the carpet and just estimate the probability that it hasn't been visited after the mixing time. So we don't quite estimate the unvisit probability, but we estimate the unvisit probability after the mixing time, or if you like, starting from stationarity. The idea is that if the graph is rapidly mixing in logarithmic number of steps, it can't do much because it can only visit log vertices. So you know, that's neither here nor there for these big numbers like n log n, so n log n plus or minus log n. And once again, it turned out that the hitting time, I mean, the problem for random walks, in a sense, is to estimate things like the hitting time. How long does it take to get from one vertex to another? And the hitting time from stationarity, it turned out, was a well-known quantity, which is it's basically an infinite sum of the difference between the probability you're on the vertex and the stationary distribution divided by the stationary distribution of the vertex. So this quantity here is the expected hitting time of a vertex starting from stationarity, you know. So basically the walk's in stationarity, how long does it take to hit the vertex? And you can turn this into something which is that you can deal with, basically. On the bottom is the stationary distribution, you know that. On the top, there's this thing RV, which is just a function of the structure around the vertex. And this RV is the expected number of returns to the vertex during a suitable mixing time. So for a walk which starts from the vertex, it's the number, so one, it's on there at the beginning, so that's 1, and then you add up how many times in expectation it comes back during the mixing time. So the walk's sort of wandering about and eventually wanders away, because if it's mixed, then the walk's got, you know, can be anywhere. So that's something you can work out. I mean, referring to the previous talk about infinite R regular trees, or Bethe trees, I think they were called. It's basically we use that kind of structure to work it out. So that's something you can work out. So then you've got something which is you can work out on the top and the bottom. So we know the hitting time, and perhaps even more amazingly, the waiting time for the first visit to the vertex tends to a geometric distribution with a success probability which is like independent with that probability. So obviously 1 over PV is E of HV. So that's it turns out that there's a lot of independence in there as long as you get the right non-visit probability.
Excuse me.
Yes?
The starting state is matters here or not from any starting state?
No, because
from stationarity.
it's from stationarity.
From stationarity.
Yeah, so what we do is we ignore what happens before stationarity. Well, it doesn't have to be exact stationarity.
But this really matters. So you cannot say the same statement about starting from a fixed vertex.
No, because, well, you can say for vertices which aren't near it, but for vertices which are near it, I mean, then, you know, there's a good chance that the walk will visit them. So it's from stationarity. But the argument we use, the argument we use is that if the mixing time is logarithmic, then the number of vertices visited during the mixing time is logarithmic. So basically, adding a log to an upper bound doesn't matter, and you can exhibit some set of vertices which are far from each other and from the start of the walk, which are always unvisited. So you can construct upper and lower bounds using that technique. But basically, it's from stationarity. Okay, so the unvisit probability is there's some mixing time, which is basically we usually think of it as logarithmic. Pi v is the stationary distribution of the vertex, or the stationary probability, because pi is the stationary distribution. Rv is the expected number of returns to v by the walk during the mixing time. So it's not by the walk, it's a walk starting from that vertex. So it's how many times, if I set out from the vertex, do I come back? So if you've got something recurrent like a grid, then that's something tending to infinity, whereas for a 3 regular tree, this has a constant value. You come back a constant number of times in expectation, and then you're anywhere. And so the unvisit probability is the probability that you don't go to some vertex from the mixing time up to time t. So it's after the mixing time, yeah? And basically it's 1 minus, it's just like it's basically 1 minus PV to the number of steps is how it turns out. So 1 minus PV is like e to the raised to the power of t is e to the minus t, that's PV there. So it's e to the minus t pi v over RV. And so that's a nice thing, because that's a number, that's something you can actually plug in and make calculations. It's not an expectation of anything, it's actually a probability for a vertex. So if I pick a particular vertex, I can say the probability that vertex hasn't been visited after the mixing time up to step t is that. So it decays exponentially with time. And this is true, holds for many types of random graph models or expanders, all sorts of things where you can get a handle on the structure, like if it's locally tree-like, the vertices for most of them. Also things, graphs where the minimum degree is high, but for random graphs you can estimate R of V accurately from the graph structure for most vertices and bound it for the other vertices. So basically you can, the stuff which you don't like, you can sweep under the carpet in this process. So that's our basic thing, because this will give us the vacant set, because I just multiply that by the number of vertices, or the number of vertices for which we have, well, add it over vertices, and that's the expected size of the vacant set at any step. So that's the basis of our calculation. It's just that we didn't realize at first that this was something you could do. So as an example, R regular random graphs, how to calculate RV. Well, if the vertex is tree-like, at any step you come back to the vertex with probability 1 over R from a neighbor, and you head up to away from the vertex with R minus 1 over R. So that's like a biased walk on the half line with probability go left 1 over R, and go right R minus 1 over R. And you can, the expected number of times you return before diverging to infinity is R minus 1 over R minus 2, which is where that number came from in front of the cover time, or 1 over the number. So it's something which can be calculated from the graph. So the more regular the structure, the easier it is to calculate RV, the easier it is to calculate the size of the vacant set. Okay, so for an example, for our regular random graphs, stationary probability of each vertex is 1 over n, because they've all got the same degree. Mixing time is order log n for most of them. Most vertices are locally tree-like. For such vertices, that is asymptotic to that, 1 plus the low of 1 times that, as that's the expected number of returns to the origin in an infinite R regular tree. So it's something well understood. So basically, the unvisited probability is you just take that stuff and plug it in here, and it gives you that. So it's just a function of the degree of the graph. So the vacant set at any step t is the expected size is just n times that probability there. Okay, so RT is the set of vertices not visited by the walk at step t, the set of red vertices, and the size of the set is just, in expectation, is just that times that. And you can use Chebyshev if you fix a t, you can use Chebyshev to prove concentration of that. So, and it's monotone decreasing over time. So we know the size, we know the expected size of the vacant set, and we can prove concentration of it. And then so now we need to find the structure of it, or the structure of the graph induced by it. Okay, so this is something we got for free from studying random walks, and then it occurred to us that vacant set was an interesting problem, and it's like most things, when you look, a lot of other people have also been interested in it, and there's a lot of work on it. But it's a cute problem. What does it look like as you sort of gnaw this thing away? What does what's left look like? Okay, so the component structure of the vacant set for GMP. How can you do this? Basically, if you consider, let's suppose that the vacant set or the unvisited vertices have got size n at some step, then and the edge probability in the original graph was p. Well, the vertices we haven't visited, we certainly don't know anything about the edges between them. So basically, that graph is a G capital NP, and once you know that, if you can find out n and you know p, then you can, as it will be say on the next slide, you can equate np to 1 and find the threshold for the thing dropping to bits, because that's the connectivity threshold for a random graph. Okay, so all we need is a good estimate of this thing as t varies, and then put it in here and find when it's equal to 1. And we know how to estimate this because we discussed it on the previous slides. So to get the vacant set, put p equals c log n over n, and we didn't probably look too closely at the c in the upper limit, but the expected size of the vacant set is sum over vertices, the the stationary distribution of the vertex times returns to the vertex. And, these vertices have got a degree of log n, or at least a constant times log n for the values that we look at. So once you leave a vertex, the probability of coming back in a few steps is 0, because you're not going to turn around and come back down 1 over log n edges. So that RV is very easy to calculate. Most vertices have average degree, so we can stick 1 over n in there. I mean, this is only a summary, but you can put pi v equals 1 over n for most vertices. So all we need to get is that. And, okay, well, the probability of retracing an edge at the next step is 1 over the degree of the vertex, which is little o of 1. So RV is, you start on the vertex, so that's got a 1 for that. Plus, you come back in the mixing time is a little o of 1. So that the vacant set is just ne to the minus t over n. That's the size of the unvisited, or the expected size of the unvisited set. And if you fix, a value of t, you can use Chebyshev to show that it's concentrated. And the thing about the vacant set is it's decreasing, so you don't have to look at it at every t. You can just look at it at some intervals. And then between it's decreasing between this one and the next one. So if it, okay, so then we chose a kind of a magic value here, which is that's the value from the previous slide. So it's just n log n plus 1 plus theta log c. So if you put this value into here, then what you get is you get n over c to the 1 plus theta log n, because the log n the n in the t cancels. The log n is e to the minus log n is 1 over log n, and e to the minus log c 1 plus theta is c 1 plus theta. So that's 1 over c theta times the probability. So that's the expected size of the vacant set. And all we're going to do actually is multiply that by p, and it becomes 1 over c theta. And then you just put theta equal to 0, as we'll see on the next slide, and you get a 1 there. So, okay, this is just pulling this stuff forward from the previous slide, but the important thing is that the vacant set is size 1 over c theta p. So remember, it's a random graph with vertex size. This is n, it's capital N, it's vertex set. So I want to equate that to 1. So NP, capital NP is 1 over c theta. So NP is 1 when theta is 0. So the threshold is around this value here. And if I let theta decrease a little bit, it will be above the 1 over n value. So it'll have a unique giant component as a random graph. And if I let theta increase a bit, then it will be less than 1 over n, so everything will be trees plus maybe a few cycles, and all components are logarithmic size at most. So once you know how to do the vacant set, you can get GMP quite easily, and this is the answer to the previous question, really. The size of the giant is of order the number of vertices in the graph. So as t tends to t from below, the size of the giant is about 1 over p, which is n over c log n. So as c gets big, we didn't really want to work this out, because at some point this is going to be smaller than log n, so we didn't want to have this conversation. So we didn't look at the upper bound very carefully here. We just said, let c be a constant or tend slowly to infinity. And above the t-star value, the max component size is logarithmic. So that's basically the end of the story for GNP. Basically, it just depends on the size of the vacant set at the threshold. The size is 1 over p. So it's not a giant component in the sense of the original graph, which is n, but it's a giant component of order n over c log n, being the size of what is left at the time. And if you make c too large, like for example, c equals n over log n, then this is basically, that's smaller than this. So some problem occurs when c is too large. And just the second part of the talk, I think this is probably going to finish before 2:30, but the component structure of random R regular graphs for R greater than or equal to 3 constant. So once again, we do the same thing. We work out the size of the vacant set. It's just given by the sum over vertices of this probability that you haven't been visited. Things regular, so the stationary probability is 1 over n. For most vertices, they're locally tree-like, because that's what random regular graphs look like for R constant. So that RV is R minus 1 over R minus 2, which is just something that you can work out from random walk on the number of returns to the origin on a semi-infinite line with a biased walk. So that's the probability that a vertex is unvisited, more or less. So the vacant set is just n times that. And you can get similar bounds for the little o of n non-tree-like. So by non-tree-like, I mean there's a cycle within some depth of its neighborhood. But it's got some precise definition, which I won't go into here. Okay, so that's the threshold, or the sort of our crude threshold. And repeating previous slides, we didn't look too carefully at the epsilon, but for 1 minus epsilon, where epsilon is some small constant or tending slowly to 0, it's supercritical, and above that it's subcritical. So at this point, the size of the vacant set at that point is, if you put t equals n, then the size of the vacant set is n e to the minus some constant times r minus 1 over r minus 2. So it's a giant component in the properly accepted sense of a random graph. So the giant component is order n, omega n. And that. Okay, so what we want to do is we want to get the degree sequence of the vacant set. So how do we do this? So this is the slightly messier part. Well, the easiest way to do this is to generate the graph in the configuration model using the random walk. So we let the random walk generate the graph in a way which I'll describe in a minute. But basically, in the configuration model, there's edge pairings. So when a walk makes a transition along a new edge, it's the other endpoint of the edge is random because because we don't know where the other endpoint of the edge is over all non-matched configuration points. So that is the next. When we walk along that edge, we expose the next edge in our random configuration, and we can keep doing this for as long as we like. We don't need to go to the end because we're just looking for this T star. So, and if we look at the the unvisited set, once again it's random, but it's random conditional on its degree sequence. So we need to estimate the degree sequence of the vacant set. And to do that, we also have to estimate the number of unvisited edges, but that can be done by the same techniques as I discussed previously, because you can do the kind of the cover time, edge cover time of graphs using, by random walks in the same way as vertex cover time. Once we've got the degree sequence, there's a Malloy-Reed condition for the existence of a giant component in fixed degree sequence graphs. So we can use that degree sequence to see whether a giant component exists or not. And the subsequent work of Czerny, Teixeira, and Windisch was to use rather more recent results by Malloy and another researcher about this, more precise versions of the Malloy-Reed condition to get results very closely in the scaling window. And we can also estimate the number of small unvisited trees in the configuration model, because the unpaired vertices are random, and you can add up the probability of a pairing in what's left. So the degree sequence, this is the size of the vacant set from the previous thing. So the degree sequence actually is just a binomial with some peculiar probability. At any step t, it turns out the probability that I'm unvisited and the probability that I've got S unvisited neighbours, so that means R minus S of my neighbours are visited, because a particular vertex is unvisited. This is unvisited, and then it may have some unvisited neighbours, and it may be that some of its other neighbours, we don't know, but it's got other neighbours. If its degree is 4 or 5, it's got 3 other neighbours. Then it's going to have some unvisited degree and some visited degree. And it turns out to be a binomial, so it's just the size of the vacant set, and then the degree of the vertex. S is the unvisited, so it's like p to the s, 1 minus p to the t minus s. And that p is this, which is very similar to that, but it's obviously been changed slightly for certain reasons. And the range of validity of this proof is from little o of n up to order n log n. So that includes our t star that we're interested in, with the collapse of the giant. In fact, most of the problems are to do at the start, or because of the problem of not being mixed, and at the end when there's not much left. Okay, so uniformity, well, if I make a random walk and I use the walk to expose the graph, so I make a random walk, this is my vacant set, and I know its degree sequence, then what's inside that is just the random graph G vacant set D degree sequence, a random graph with that fixed degree sequence. Because basically the walk's revealing the graph, so everything that the walk doesn't walk on, we don't know anything about, and we certainly don't know anything. Given the degree sequence of the vacant set, we can, if G wants one random graph on that vacant set, we can swap another one in and it won't make any difference to the history of that walk because the walk didn't go there. That's all we need actually is all we need is we need to calculate the degree sequence of the vacant set. And high probability, so we need some high probability estimates of the degree sequence of the vacant set. And then the rest of it is automatic. So we've got the vacant set. You can also calculate the number of unvisited vertices. We need to calculate the degree sequence. Okay, the annealed process, this is not the annealed process, this is our annealed process. So we use a random walk to generate the graph in the configuration model as a random pairing. So at some time we've paired some of the configuration points, so they're blue. So I'm using the word blue and red in two ways here. So a visited vertex can have unpaired edges. It can have, some of its edges are not visited, and they may match with unvisited vertices, or they may match with other visited vertices. So when I've matched T a certain number of edges, a certain pairing at time T, then I've got some unmatched points, and if I know roughly how many edges are unvisited, I can basically know the size of those sets, because I know I can estimate this and this for any T, because I know how many edges are unvisited, and that's this thing here, because unvisited edges can be between visited vertices, and I know how many are visited. So these are known quantities. So visited vertices may have configuration points in RT corresponding to unexplored edges, but that's not a problem because you can estimate the number of those. So the next configuration pairing, I'm sitting here. Where will I go next? Well, I've got quite a lot of choice. I pick an edge uniformly at random. So the probability I pick a blue edge is 1/3, and the probability I pick a red edge is 2/3. And if I pick a red edge, in other words, an unused configuration point, I can either go to a previously visited vertex, or I can go to a completely unvisited vertex. So the probability I go here is the degree of the vertices in the unvisited set times its size, because all their edges are unvisited, divided by the remaining number of configuration points minus the fact that I've picked that one. So and this can be worked out from the number of unvisited edges. So you can work out the probability that you go to an unvisited vertex at the next step. Okay, so that's basically everything really. I'll explain some of the details of how it's done. It's a bit messier from this point, but I won't go into too much detail. But everything, as long as I know the number of unvisited vertices and the number of unvisited edges, I can work out everything in the configuration model. Okay, so shrinking vertices. There's a slight problem with random walks because there's this, what we want to know actually in what we do is the first visit to a set of vertices rather than just a vertex. So Our technique doesn't really work very well for that as it stands because of certain technical details, but what you can do is you can just, if I want to know what is the probability that I visit A or B, or both A and B are unvisited, what I can do is I can just coalesce them to a single vertex and work in the graph with the set coalesced to a single vertex. So this is a standard technique sort of for working with random walks. So I get a set of vertices that I want to know if they're unvisited, and I just shrink them to a single vertex. So, for example, I might want to know that some particular tree is unvisited, so I can shrink it to a single vertex, and I can make a graph. I called it H of G there with these vertices shrunk to a single vertex, and the probability that S is unvisited at step T after the mixing time is about the same as the probability that the contracted set is unvisited after the mixing time. There are some slight differences because the mixing rate is slightly faster in this, but it doesn't make any difference to our proofs. So I've got some vertex, here it is V, and I want to know that these three vertices are unvisited and these two are visited. So basically, if I take some set of vertices and I contract them, I can get the probability that that entire set is unvisited. And on contracting them, then I'll get some edges sticking out of that vertex and some loops inside. So there are some number of, there are 17 edges sticking out and 3 loops inside the, or 14 edges sticking out and 3 loops inside that contracted vertex. And by using inclusion-exclusion, I can ask the probability that, the probability that that is unvisited and the rest are visited is a kind of inclusion-exclusion on that's unvisited and that's unvisited, and so on and so forth. You can sort of get all the subset things and do inclusion-exclusion on it. So basically, when you do that, you get this, the probability that vertex is unvisited is the probability that that times that binomial thing. And that binomial thing is got by taking all possible exclusion-inclusion sums over those vertices plus these ones, which is a bit messy, but it doesn't really make any difference for this technique because this technique, you just contract vertices and take their degree, okay? So you can calculate the unvisited probability of any small set in this way. So when you take those, so this is a vertex. It's red neighbours plus some other set. It's just the total degree divided by the total degree of the graph, and this thing can be calculated. I'll show you a sort of example in a minute. Because basically it's either an R regular tree outside this thing or it's a loop. If it's a loop, it comes back with probability 1, and if it's on a tree, it's doing what it normally does. So this can be done in exactly the same way as as everything else. So there's no problem with it. So here's an example, right? So I want to know if they're unvisited. So I can just take them, I can contract them. So those 3 edges become loops. So the thing, when it's left over, look, it's got a vertex with 3 loops and 14 edges sticking out. So if I set out from here, and I go down here, which is 6 over 20, I come back with probability 1. And if I go down there, I come back with the probability of a biased random walk on a line. So that formula is just the combination of that stuff from there. So it's kind of straightforward. And you put it into the inclusion-exclusion formula, and what comes out at the end is this thing here with these binomial probabilities and this peculiar value. It's just a product of, adding it all up, which can be done. So at that point, you've actually cracked it, because now, and that's just reminding you of that again. So at that point, we know the degree of everything, because the expected number of vertices of degree S, red degree S and blue degree R minus S, is just that. This is a known quantity, so the total number of things is just n times that. So we've got a random graph with that degree sequence, and then you can put that into the Malloy-Reed criterion, which is basically you add up the degree times the degree minus 2 over all vertices in the graph, and if it's greater than 0, it's got a giant. and if it's less than 0, it hasn't got a giant. So that's basically, you do that, and you get this value of t out the end. This is what comes out when you equate that to 0, adding over that. And that's the threshold value. And that value of t, you can improve this condition by getting a much more a finer version of it, which is what was done by Czerny, Windisch, and Teixeira to get the scaling window. But we just did it rather crudely and sort of said, well, it was a little bit bigger or a little bit smaller. And that value of t has actually got a very sensible meaning, because it doesn't look very sensible. I mean, it's something, you know, some r's and some logs times n. But the probability that a vertex, an unvisited, if I'm unvisited, the probability my neighbour is unvisited for a particular edge is that. So if I'm sitting here and I go to, I basically want my branching factor. The walks come to a vertex, so it's got r minus 1 other edges. I want my branching factor to be at least 1 for it to be a branching which survives. So if I multiply the number of outgoing edges, so the walks come into the vertex, I take the number of outgoing edges, multiply it by this probability that my neighbour's also unvisited, and that has to be greater than 1. So when you equate that to, you take that value and put in that, it comes out to 1. So it's just behaving like a branching, you know, just like an ordinary sort of Galton-Watson process at that point. And this, so this is kind of like the percolation threshold. Okay, and then all you've got to do is count up the number of small trees. So this is this actually comes from what we did previously, but at this point you need to remember that really they are small subgraphs of an existing graph. So how do you count small subgraphs of a given graph? Well, it's all right if basically that graph is like a tree, because I can, if I'm sitting at a particular vertex, the root, I can count up the number of subgraphs of size 3 here. It can be enumerated using a generating function. So there's 3 subtrees of size 3 which are like this and 2 neighbours, and 6 subtrees which are like that and 1 neighbour and the next neighbour. So that can be added up. So that's just a formula for the number of rooted k subtrees of an infinite R regular tree. So that's like the number of them, and then you can get the probability that that's visited and all that is unvisited and its neighbours are visited, and multiply them together, and that comes out as a tree census. So this is basically that formula divided by unrooting the tree times the number of sets of that size by the previous calculations. So at this point it's almost over. I know they're messy formulae, but it is a kind of, you know, it tells you how many trees there are in these things. So you know exactly what it looks like. You can say it's got this and some little trees and so on and so forth. So just as an example, if I take this value and I calculate the expected proportion of vertices on small trees by as that tends to as it increases from 0 to its maximum value of that from this formula, which, because you can't really, but you can evaluate this in Maple or something, and you plot it, then it kind of goes up to that point and then drops down like that. It's got a kind of cusp on that formula. And we know the size of the vacant set. So just as a sanity check, if that's the vacant set and this is the t-star threshold, there shouldn't be anything but trees after this point. So when I superimpose that on that, it should basically they should fit perfectly. And in fact they do. So that's that curve evaluated for r equals 3. So that's the number of isolated trees increasing, and then the giant crumbles, and then the whole lot is trees, and it kind of goes down again. So that's the kind of the story of the vacant set for r equals 3 as time progresses past the t-star value here. And at time n log n, or 2n log n, it's completely visited. Okay, so closing observations. Apart from the fact it's not +1, but this is as much as the talk is. For the classes of graphs GMP and random R regular graphs, there's threshold behavior. And Schnitzman and people have established that there is threshold behavior in toroidal wrapped grids for at least 3 dimensions, and there's clearly no threshold behavior in 2 dimensions, because from those simulations that, or maybe there is in the limit, but nobody knows. The size of the giant can be estimated in the supercritical range. The number of small components can be estimated. The technique is simple, in inverted commas, compared to random interlacements, but seems restricted to random graphs, because basically you either need to know, like in the case of GMP, or you can do the directed equivalent as well for strongly connected digraphs and get the, you can do the DMP equivalent of this. You either need to know that the size of the vacant set and then just use the fact that everything inside the vacant set is random, or you need to be able to calculate the degree sequence of the vacant set. And the only way we can see of calculating the degree sequence of the vacant set is revealing it in a configuration model using what we call the annealed model, which isn't the annealed model, it's our annealed model. So thank you very much.
Thank you very much, Colin, for your very nice talk. Now it's time. We have plenty of time for discussion. You can ask almost any number of questions.
I would get almost any number of answers.
Yes.
Or not.
Does it work? Oh, now it works. Okay. Sorry.
I have, since we have time, I have two questions.
Oh yeah, okay.
So the first question, can this technique be extended to a general configuration model? What do you think?
Okay.
If a degree sequence is given,
Yeah, yeah.
or is drawn from some distribution?
Okay, I'll tell you what the problem is there. Maybe I'll just back this up a bit, yeah. Okay, so the problem is that if you take a general, I mean, you're thinking, oh, let's just take most of the vertices constant degree, and
Well, better we'll take some skewed distribution.
yeah, okay, some skewed distribution. Yeah, okay. The problem is that
Yeah, the difficulty in estimating.
this is the problem. I mean, for things, I mean, you can do this RV on all sorts of things, like you know, very symmetric graphs. They don't have to be random. So things like hypercube, because it's so symmetric. Anything where you can estimate this, or if the minimum degree is tending. So if the minimum degree was tending to infinity, no problem, because you wouldn't have any returns. No, we don't know how to estimate that really in that model. So we don't know.
Maybe it's possible.
Yeah,
but
maybe it's possible.
At least you,
yeah.
at the
I mean,
moment you
but
don't
you'd have
know.
to you'd have to get. I mean, it's going to be RV. RV is going to be have some distribution, and then if you know what it is, and it will depend on pi v, and you can. You can chuck that in and add it up probably. In principle, but you'd have to sum over all the vertices rather than just multiply it by the set size. Yeah, because to be quite honest, going back further. Okay, this thing here is like a preferential attachment graph. I add 2 edges at each step. Yeah. So, okay, that's all over the place as well. But for that, the kind of the RV which determines the cover time is basically vertices with degree 2, whose branching structure is got a degree 2 branching, right? So the thing which the blocking structure for the cover time in that is this. So everything else, so more things which are more branchy, yeah. So things where you got higher degree, more things have hit it in the past. So this is really like, you can orient that like that. So this is the kind of the basic blocking structure. So, and we basically had to prove that, because otherwise we couldn't have done that, because we just proved this was worst and this was covered last, so we didn't have to bother about anything else. But we've thought about that on several occasions, and yeah, we don't know is the answer, because it's actually an interesting question. Yeah, if you could, I mean, it's actually an interesting question, you know, what that RV is, yeah, for the fixed degree sequence, yeah. Because then, I mean, then you could do a lot of things. I mean, you could do vacants. You could crawl around on the giant component of a random graph, something like that, you know, and work out its fate. You can do a lot of things, yes, but we don't know, because we don't know how to do it. Yes.
I have time for another question.
Yes, yes.
So, can you outline the proof of this lemma that the visiting time is exponential after starting from the... If we have time.
Yeah,
if we
no,
don't have time, so maybe we can leave this question to the end. If we don't have any more questions, you can answer this question.
Well, I can show you where it comes from. But okay, this basically comes from this. It's if you go to the chapter in recurrent processes in Feller Volume 1, basically if I'm at a vertex at a time t, then basically I made some first visit to it at some other time, followed by a return at some time. Yeah, so the generating function for that is equal to that times that. Yeah. Okay. So, I mean, of course, what you want to do is you then want to divide them through, yeah, to get the first visit generating function. Okay. So, well, you don't really know what this is, but the point is that after a certain time, which is after the mixing time, those, if this is vertex v, then that after a mixing time, the coefficients of that are just stationary probability of it. Yeah. This is my probability that I'm on. I'm on vertex v at time t, starting from somewhere, vertex u. Yeah. Now I don't really want to deal with this early on, which is why I don't start asking until after the mixing time. But after the mixing time, PV is pi v. Okay? So that is just pi v z to the mixed time over 1 minus z. You can add it up. Everything, from mixing time onwards, everything is just pi v z to the t greater than or equal to t. So it's almost, you know. You have to have quite a good mixing time. And this also, after the mixing time, well, you separate this into two parts. The first part, so you write r of z as rt of z. So that's the generating returns up to the mixing time, which is where the rv comes from. Yeah. And after the mixing time, well, it's pi v z to the t plus pi v z to the t. It's not exactly that, but it's of that order. Yeah. So basically, you can write that as rt of z plus z to the t pi v over 1 minus z. So when you take the ratio of those things, you can clear the 1 minus z's. So the ratio of that h of z is equal to, f of z. F of z is sort of equal to basically h of z, which is pi v z to the t, and I'm going to multiply through by 1, so it's rt of z, 1 minus z, plus pi v z to the t. So that's where putting z equals 1 in here is, then you just find the smallest positive root of that, and that's the, you basically extract the coefficients of this. And so this is where this, so basically basically the smallest positive root of this is at 1 plus PV. Okay, that PV, where PV is RV over pi V. So this, I mean, that's where that RV comes from. You can really think of that as Z as 1. So you can, but it's not quite 1. So you get RV times minus PV there and some stuff here. Yeah, it's extracting coefficients of generating functions, asymptotics. So the trick is to get rid of everything by putting stationary distribution. So it's just it was just a bit of luck. We just,
What are the most general conditions for this lemma to hold?
well, the mixing time, well, okay, the problem is the longer the mixing time, the more you're going to have trouble adding that up, because there are some conditions, right? When you do this, there are a couple of conditions. One is, but the main condition is that this is just checking that there aren't any roots in some circle, right? Which is not very nice. We're not very good at that. So you have to apply some Richet's theorem, but you have to do it in quite a fiddly way. Yeah, I mean, we tended to focus on sublinear mixing times. Basically, we're thinking of logarithmic, or you could do square root of n. I mean, you can do three regular finite grids, because the mixing time is like n to 2/3. So you could do that, but you can't do two regular grids very easily, because the mixing time is basically n or n over log n. It doesn't.
So the main condition is significantly short mixing time.
Yeah, yeah, that's right, because basically we've and also the problem is, you see, that we've ignored hitting before the mixing time. So if you've got an enormous mixing time, like order n, okay, well, you know, I've got the probability it hasn't been hit after here, but, you know, the probability of hitting a vertex in here is large, right? Because, I mean, that vacant set is the ones that haven't been hit after the mixing time. So there's, before the mixing time, it may be that some tiny part of that vacant set has been hit, yeah? But it doesn't matter for our calculations, because we can throw away a little bit. But if you've got a huge mixing time, then part of your vacant set has been, a big bit of it's been hit. And so, you don't know, you can't calculate the probability that, well, you can't get it as an explicit formula, apart from a matrix formula. If you've got a huge mixing time, the probability that you haven't been hit in that time. It's, well, you might be able to, but we can't, okay?
Thank you.
My question is closely connected with the previous one. What technique do you use to estimate mixing time in preferential attachment model? It is not trivial, because you estimate, as far as I know, log of n.
Yeah.
It is a mixing time estimation in this model. It is very fast.
It's not log n in the preferential, is it? It's like log squared or something, yeah?
Excuse me?
I think you can have log squared in standard preferential attachment.
On slide, I saw covering time n log n, hence mixing time log of n number of vertices in the graph. Yes?
I didn't say the mixing time. Did I say the mixing time of the preferential attachment model?
Yes, mixing time in preferential attachment model.
Well, that wouldn't be true, because it's probably log squared, isn't it, or something?
Oh, yes, here we have covering time, and
this is a cover time of the preferential attachment model, but the mixing time is log squared, I should think.
log square of t, or
Log t is log squared of t. I would think. I wouldn't think it's log, but that doesn't make any difference. It's not n anyway,
I see.
because in log squared steps, you're not going to visit many vertices. You visit log squared vertices, if you're at the most, yeah? So it doesn't, our calculations are, these cover times are calculated as follows. An upper bound using the vacant set after the mixing time. So that's an upper bound, followed by explicitly constructing a set of vertices which can't all be visited in 1 minus epsilon times that. So you can throw away quite a lot. So that those sets that we construct are sort of like n to the half. So you can throw away, okay, so that's basically where it comes in for the construction of the lower bound, because you have to construct a set of vertices which haven't been visited. So, and normally what we do is we take vertices which are far from the start vertex and far from each other. So it's like a kind of sprinkling of vertices over the graph, far from each other. And then we prove that there's slightly less than the cover time, there's always some which are unvisited with high probability. So and so you have to be able to construct a set which is larger than the mixing time. In fact, when you look at the statement of the lemma, actually you need like polylog times the mixing time. So you're throwing stuff away all the time. So there are conditions which come to play in this, but essentially you need you want a sublinear mixing time, well sublinear, and you need to be able to construct a set of vertices which are far from each other, which you can prove haven't been visited in sort of slightly less than the cover time. So that set has to be quite large because even if they're hard to visit, there has to be more than the mixing time because you have to throw those away. So there are technical things in there when you do the
It's
details.
your estimation, yes?
Huh?
It is your estimation.
Yeah, our estimation. Yeah, that's the way we do it. The upper bound comes from that, multiplying that by n, essentially. So the expected number of unvisited vertices. So when you put in the cover time, that will tend to 0. It's less than 1, and then you have to construct the lower bound separately because this is an upper bound construction.
One more question or comment? Please use this microphone.
Aye.
So thank you very much for the interesting talk. I have a little bit of technical question. If you could come back to this cover time slide.
Yeah.
I'm really sorry for this question, but so the question is, you often use this this wingle, this sort of like asymptotic equivalence sign, this little wave, yeah. So when people use this wave, they sometimes mean different things by this. So I wanted to ask, in particular case of this cover times, what kind exactly of asymptotic equivalence do you mean?
It's just basically, if I took it's just the ratio tends to 1. I mean, this is like what we've got is you've got the cover time is 1 minus little o of 1 times that is less than or equal to the cover time is. So basically, the way we used it is I would just think it just means the ratio tends to 1, doesn't it, in the limit?
Yeah, it does, but
so basically, we've got the cover time is less than or equal to like r minus 1 over r minus 2 n log n 1 plus epsilon, where epsilon tends to 0 is less than or equal to minus epsilon. That's all we mean.
No, but then there's some probability because cover time is random.
It's an expected value.
As expected value. Oh, okay.
But you can prove actually that for these sort of things, it's concentrated.
Yeah, of course.
Yeah. I mean, those. Well, it's certainly concentrated in the upper tail because if you start cranking that value of t, anything up above the cover time, this is dropping off exponentially, yeah, fast. So yeah, it's definitely concentrated in the upper tail. The lower tail is trickier because it's a constructed bound.
Okay. Okay, but there it's just expectation. That's why
it's an expectation, yeah, but
okay.
It's certainly concentrated from above. So I suppose that means it's concentrated from below as well. But no, I mean, when it's stated as an inequality. I've just extracted, because there's enough junk in here already, you know what I mean? I can't put equals, right? So I have to put something. If I put proportional to, then it's, where's the constant? So
Yeah, exactly.
I can't leave just a gap there. Yeah, no, it's just been simplified for it's a less than or equal. We know the rates. We have estimates. We have estimates of rates, and they're not perfect, but.
Okay, thank you.
Okay, thank you once again, Colin, for this wonderful talk. Now we have a break for lunch, which is until 3:30. It's possible to use the cafeteria of Yandex, which is just in front of this entrance, which is very close to here. Maybe I can just take 2 more minutes asking Colin, could you please advertise a little bit your talk on Monday? Maybe it's also useful. I'm sorry.
Okay, so apparently I'm giving a talk on Monday as well. How can I explain this? So they said, would you give a talk about web graphs? So I said, well, we haven't done anything on web graphs for years, so no, I'll talk about something else. But then Andre insisted, right? He said there are some so it was a bit difficult really, because like the last time I gave a talk on web graphs, it was transparencies, so I had to basically rewrite it. But it's okay, it goes a bit further since then actually, but it's like a scale-free graph model that I worked on with Alan Fries quite a long time ago initially, in sort of like 2003, and then we sort of we developed it in various ways, including when it's preferential attachment, but it's generalized preferential attachment. So at any step you can add edges between existing vertices, and they can be preferential at one end and uniform at random at the other. And you can have a new vertex comes along and adds some mixture of edges, uniform at random, preferential, and you can do. There's a directed model as well, a sort of Hubble authority model, and so it's a very generalized preferential attachment model with a directed model and various things. And you can also let the number of edges added at each step tend to infinity, because if you add constant number of edges at each step, the power law is 3. So it's a reasonable question. How many edges, what's the edge growth have to be before you can get out of that? And it seems that you have to add t to the constant edges at step t to get out of power law 3 for preferential attachment. So that is mentioned as well.
Okay, thank you very much. Let's go for lunch.